Right, so these are the notes for lecture number 7 that we did not cover in class. I am not recovering any of the things that we did cover, things like muscle fiber type comparison. We talked a little bit about measuring human metabolism. We did talk about things specific to article number 7. But there's a few things. We also mentioned adaptations to exercise training, especially endurance exercise training. And so here in this lecture, we're really talking about muscle metabolism and how it varies, right? Some of the different things that can take place with metabolism. We're not going to go especially deep with this, but there's some basic principles that I think are relatively easy to understand. Okay. The first here and the next 3 slides all have the same title, right? I've decided to title these slides where we're talking about muscle energy metabolism. We know that there's different types of metabolism, right? We can burn different energy substrates, but that depends on the intensity of the exercise as well as the length of the exercise. And those two things in your mind should go together anyway, because you have a very high intensity exercise, you can't go very long anyway. And there's going to be reasons for that. Other than you're just going fast. Okay? And this is the way another textbook breaks it down. I kind of like it. It talks about the immediate muscle energy needs. Right now, you can go from 0 to 100 with your muscles in less than 3 seconds, and you can start to burn billions and billions of ATP. But we don't store ATP. We have to produce it. And it takes a little while to kickstart ATP generation. Okay? So it's not immediately, oh, all of a sudden glycolysis, ATP. It's not that fast. Okay? So the immediate muscle energy needs, you need a burst of activity, whatever it is going to be the phosphagen system. Now, we talked about the phosphagen system in a previous lecture. Right, just to remind you, creatine phosphate, the enzymes, creatine kinase and myokinase are the enzymes of this system. And we were able to regenerate ATP without breaking down any energy substrates like glucose or fat. Right, in this case, I give the example of creatine phosphate here, where we merely took that phosphate off of creatine because that was a high energy bond. We transferred that phosphate over an ADP. Now we have an ATP still with the high energy bond naturally, right? And so we were able to rapidly replenish ATP. We'll talk about the speed of this in just a few minutes here. Well, the phosphagen system, depending on the speed at which you go out, if you're going to go all out, you've got enough for about 6 seconds, so a 6-second sprint. If you're not going all out, you're on a really brisk walk. That's about a 1-minute brisk walk. The phosphagen system won't do any more than that. In terms of weightlifting, and I'm really trying to focus on aerobic exercise here, but in terms of weightlifting, it's the phosphagen system that actually helps to replenish the ATP between exercise sets. Okay? And of course, as you move further on in your sets, it's harder to recover because the system, of course, gets exhausted. It takes some work to replenish it. Okay, so our second one, we've gone from immediate energy needs, which is only 6 seconds sprint, to short-term energy needs. We'll define the length of that in just a moment. And this is going to be anaerobic glycolysis. So we're doing glycolysis, breaking down glucose, no oxygen, right? We're not going to use oxygen for this. Well, if you remember, this does not produce a lot of ATP, but it does produce some, right? And we need some. So here we go. And the glucose that we use for this glycolysis, muscle stores glycogen, and we can break down that glycogen and get some glucose. So here's glycogenolysis. We can also transport some of that glucose in from the blood, right? The blood, there's glucose, coming from the blood all the time, and we can start to transport that in and use it for energy. But again, this isn't going to last a long time because this is just a short-term need. But remember, the end product of anaerobic glycolysis is lactate. Lactic acid. It's an acid. It lowers pH, and it causes fatigue. So you cannot go very long on purely anaerobic metabolism. And this provides enough energy for about 30 to 40 seconds of maximal activity. So we've gone from a 6-second sprint, so at about 6 seconds, this kicks over into anaerobic metabolism, and that's going to last up to about 40 seconds, right? We haven't gone very far, right? We think about it, we have not gone very far. And I make it sound like it's this strict cutoff. They're not strict cutoffs, you know, it's kind of phasing into anaerobic glycolysis. Now we go to long-term energy needs. And there's a lot more on this slide because there's just a few more facts I wanted to bring in and emphasize. Well, this is going to be aerobic metabolism. So now glucose runs through glycolysis, but guess what? It doesn't become lactate, it's pyruvate, acetyl-CoA, enters the citric acid cycle, right? We're using aerobic metabolism in the mitochondria. We're breaking things down, citric acid cycle, the respiratory chain. And this, in addition to burning glucose, we can also burn fat, okay? Because, remember, fat can enter acetyl-CoA and also be run through the aerobic metabolism here. So the glucose, it's still going to come from glycogenolysis. It can be transported in from the blood, but now we have time to do some special things. The liver can actually have glycogenolysis as well. I'm trying to focus on muscle metabolism, but where does muscle get its energy from? It's not all from in the muscle, it's pulling it from the blood. Well, where does the blood get the glucose from? The liver. The liver stores glycogen, is breaking down, releasing glucose, and so that's sustaining blood glucose levels. And then the muscle can now use that glucose for energy. In addition, GLUT4. Remember we talked about this as the insulin-sensitive glucose transporter. Here's a situation where we actually have pools of GLUT4 inside that are not sensitive to insulin, rather they're sensitive to muscular activity. And they're moving to the membrane, and this should make sense, right? Because we need to bring in more glucose for the activity, and these translocate to the membrane, and they're in vesicles, so the vesicles kind of do exocytosis, but what was in the membrane of the vesicles becomes part of the plasma membrane. And now the GLUT4 is in the plasma membrane. And it can bring more glucose into the exercising muscle. Well, the fatty acids, muscle stores triglycerides. In fact, we talked about how type 1 fibers, which are more primed for aerobic metabolism, store more triglyceride. Well, because they can use aerobic metabolism. So you can have those undergo lipolysis. You can also transport fatty acids in from the blood. Those fatty acids in the blood came from adipose tissue. Adipose tissue is also undergoing lipolysis. And so it's breaking down fat and delivering these fatty acids to the exercising muscle, which can then use them for energy. Now, going backwards just a little bit here, the end products of aerobic metabolism, right? Carbon dioxide, water. Water, perfectly innocuous. Carbon dioxide, right? We can breathe it off. We can get rid of it. This is to maintain aerobic, you have to have a lower intensive activity. And we can just keep breathing that off. You might be breathing harder, but you've got to get rid of that carbon dioxide. So this takes over after about those 40 seconds when the anaerobic metabolism is exhausted. Of course, if you're doing maximal activity, you still won't go very long because this is slower, as we'll see in a minute, and it can't keep up. But if you slow down your pace, you can obviously go much longer, and we'll have some graphs that kind of illustrate this. Because if you maintain a lower exercise intensity, you can go for days and days on aerobic metabolism. So shifting thoughts here, there's something known as the anaerobic threshold, and I've written out a definition here. There's an exercise intensity, and if you keep increasing intensity, eventually you switch from aerobic metabolism to anaerobic metabolism. And we're not saying from 100% anaerobic to 100% aerobic, but you can see something like this. So on this, lost my cursor, on this axis down here, exercise intensity, all right, we're going to slowly increase exercise intensity right here, right here, right here, right here, right here, right here. And all of a sudden right here, let's say you switch to anaerobic metabolism. And we're going to have this switch right here. Okay? And this is a visible thing. And we can determine that kind of in two ways. Sometimes this, so that would be the threshold, right? The anaerobic threshold. Sometimes it's referred to as the ventilatory or respiratory threshold, and the purists are going to get mad at me because this is what's happening at the lung level, right? Your breathing rate goes up. So if this is respiratory rate was going up with exercise intensity, and then all of a sudden there was this sharp increase, and that's because it hit this anaerobic threshold, and now we're breathing a lot harder and a lot faster. In addition, it's also, there's probably a better way to say it, this also corresponds with what is known as the lactate threshold, because switching to anaerobic metabolism, now remember it's anaerobic glycolysis, the end product is lactate, lactate starts to build up, it spills over into the blood, and so this is actually also accompanied by an increase in blood lactate levels, which is what I put in the y-axis here. So again, blood lactate levels, my curve here is actually probably a little bit too sharp. It just barely goes up with exercise intensity until you hit this point right here where all of a sudden lactate starts to build up in the blood much faster. And again, that corresponds with that respiratory threshold, and there's reasons for that because we're trying to blow off. Acid stimulates breathing, and CO2 we're producing more of. Anyway, that's stimulating more breathing. But we also have that buildup in lactate levels because we've switched to anaerobic metabolism. Okay, so that's the anaerobic threshold. All right, so we're switching topics here. And this is really the only slide I have on this particular topic. My pen did not work here. Let's try this again. There we go. So we talked earlier in the semester about hormones that regulate metabolism. Well, there's changes in these hormones when it says during acute exercise, like during an exercise bout, right? And again, generally this is referring to more aerobic style exercise. And remember, we had insulin, epinephrine, glucocorticoids, and glucagon. And insulin was a storage hormone, whereas epinephrine, glucocorticoids, and glucagon all mobilized fuels. Okay? So think, during exercise, what do you want to do? You don't need to be storing anything, right? So insulin goes down, whereas epinephrine, glucocorticoids, and glucagon, because they're mobilizing fuels, they all go up. And a moment ago when we talked about how liver glycogenolysis will go up during exercise, well, it's because these hormones are going to cause it to go up and break down, form glucose, and then secrete it into the blood. And we also mentioned how adipose tissue starts to undergo lipolysis. Well, that's an effect of epinephrine. Epinephrine stimulates adipose tissue lipolysis. So it'll break down, releases fatty acids into the blood. Those fatty acids can then be taken up by exercising muscle. And so this is all linked into exercise metabolism as well, even though we're trying to focus on skeletal muscle. Right, this particular slide, note here that we have exercise intensity again on the bottom on the x-axis. And then over here on the y-axis, we have percent contribution to total energy. So we're looking really at fat and carbohydrate as energy sources. And more specifically, we're looking at the non-protein, right? We're not considering protein here. And we talked about that when we talked about RER as well. So down here at a very low exercise intensity, okay, right down here, look, you're not burning, here's the carbohydrate line, right? And here's the fat line, and I did my best to draw lines, but it was free-form by hand. And you're not burning a high percentage of carbohydrates at a low exercise intensity, but you are burning a high percentage of fat. But as exercise intensity increases, that percent of fat you're burning comes down, and the percent of carbohydrates you're burning is going up. And they get equal at around 60% or so, and it varies a little bit from individual to individual. When carbohydrates now become more predominant than fat, But now you're a much higher exercise intensity. And remember the idea that you're shifting at a specific exercise intensity from aerobic to anaerobic metabolism. It probably starts right about here. My lines aren't perfect, but they illustrate the principle here. All right, and this particular slide is looking at how your energy substrate. I need to change this title. You'll see a change in title before I post this. I accidentally kept the same title here. So in this one, there's two panels here, right? The one on the left here is rate of ATP generation. So how quickly, right? This is a rate. Rate is per unit time. Rate of ATP generation. And then we have it from several different sources. We have the creatine phosphate. And then we have anaerobic glycolysis. Aerobic glycolysis. So this is glucose going through glycolysis, but then it can continue on through the citric acid cycle. And then we have fat oxidation. So this is just fatty acids moving right into the citric acid cycle. Note that the rate of ATP generation for creatine phosphate is very high. But then we go down with anaerobic glycolysis, down further with aerobic glycolysis, and way down with fat oxidation. So it takes far longer to create ATP using fat than it does from creatine phosphate. But then creatine phosphate, remember, it was done in 6-second sprint, whereas fat oxidation can carry you forever, right? That's the idea here. So it's slower, but it can last a much, that's going to help you get more out of it in the end. And then our two forms of glycolysis here, anaerobic, rate of ATP generation very high, right? Because it's just going through glycolysis. But it slows down if it's going into oxidative metabolism in the mitochondria with the citric acid cycle and the electron transport chain, because that's a slower process. And in fat oxidation, that's all it has, so it's a much slower process. Now, contrast that over here to this next panel where we're looking at total ATP generative capacity. So how much ATP could be synthesized, formed, using these different energy substrates? Well, creatine phosphate, it's not very much. We can make ATP really quickly, but we're limited with how much we can do. And that's why it only lasts 6 seconds, or a 1-minute brisk walk, remember. And note, we have kind of a reverse direction here now. We're going to go like this. Anaerobic glycolysis, yeah, we can get a little more out of it, but it's not a lot, because glycolysis, you're really limited to glucose that is there, plus glycogen that is stored in the muscle, plus glycogen that is stored in the liver, right? That's all the glucose we have. That's all you're going to be able to use. And you can only get so much ATP out of that relatively limited supply, especially anaerobically. Whereas aerobic glycolysis can produce much more, but remember, you can only, from glucose, you only get like 2 ATP from glycolysis itself, where you get 34 additional ATP if you can send it through oxidative metabolism. So it should be much higher, right? You should be able to form more ATP aerobically. But then we come to the last one, right? Fat oxidation. Remember, fat oxidation, you're only running through the citric acid cycle, and we get far more calories per gram of fat, and we store way more fat than we store glycogen. And now the total ATP generative capacity, I actually did not put a top on this. It goes up through the ceiling here of your screen. In fact, it goes way above the ceiling. We can form a ton of ATP from the amount of fat that we have stored. Just remember, so we can get a lot of ATP, but it's a much slower process, right? If we compare these two graphs, we see that the rate of generation is inversely correlated here with how much ATP can be generated.